Thank you. Thank you very much. I'd like to start by thanking the Faculty of Forest Sciences for nominating me and this university for honoring me with this award, and I appreciate that very much. Thank you. I'm going to tell you about statistics. I say it's a key technology. I'll tell you in a minute, and then I'll raise some scientific questions and tell you that the answer to most of these questions comes through a particular type of measurement, a measurement of a direction. And I'll tell you how these things come up, and I guess I can read here. Huh? Okay, so my talk, as I say, is going to be of completely different flavor than what you have been hearing so far, because I'm a statistician. And what is statistics about? Briefly, I would say statistics is a set of techniques for collecting data, summarizing data, analyzing and interpreting data. That's what we all do in research. And statistics, I say, is a technology. In fact, I say it's a key technology of the present day. And what is a technology? Science, for example, helps for us to understand nature around us, laws of physics, chemistry, and so on. That's what science is about. Whereas a technology like engineering is to help mankind, invent a better car, right? Things like that. Engineers, what do engineers do? I say statisticians do that. We use science to help serve mankind. In what sense? Statistics incorporates what I call inductive logic, inductive reasoning. What we do in all our scientific endeavors is to collect some data, and we can never collect all the data that is available to us. So based on this is a major building block, I say, on which new scientific advances are based. Statisticians help scientists and others make a guarded leap of faith from the sample to the complete, the population as we call it, and play a pivotal role in the progress of science. Anytime one wants to make a careful scientific statement, statistics is the right tool. For example, recently we all heard of the God particle, the Higgs boson particle. They spent hundreds of millions of euros and thousands of hours of experimentation. But if you read carefully when they write a scientific paper, they say the results show a so-called 5 sigma of significance, which means there's only one chance in 1 million that the Higgs boson signal that the team observed is a statistical fluke. They are still admitting there's no God particle, and there's a very small chance that isn't such a particle. So, one has to be careful. They do experimentation. No matter how much you do, you can't be completely sure. So I say even physicists, they have to be careful and they have to make correct kind of statements like this. And our discipline, I say, has a lot to do with agriculture. In fact, we progressed because of this experimentations. There is a founder of statistics. One of the founders is Ronald Fisher, R.A. Fisher, and he used to work at this Rothamsted Experimental Station, crop research. And this is how a field of statistics called design of experiments came about. So we are very closely related to agriculture, and I have been involved with a number of people in the Faculty of Forest Sciences, Professor Bo Raneby, who is in the audience here, and Bengt Christom, and I worked with several students there for their doctoral work, and I won't get into that area of research because it involves esoteric equations and mathematics and so on. So what I will do instead is take you on a detour on a special kind of data and tell you about where such data comes up and different scientific questions that it helps answer. Okay, this data has to do with what I call directions. What are some of the scientific questions that I'll talk about? Did a river change its course over geological time? This is how I got started in this field way back in the 60s. A geologist comes to me and says, I observed certain flow of a certain river in India, which was there 1 million years ago. How does a geologist know how the river flew 1 million years ago? Well, they have their techniques. There's something called a sedimentary rock, and that rock, they can tell how old the rock is. and they can also tell what direction the river took at that time. So he wanted to know if the river changed its course. Is the ozone level in Santa Barbara, we are not too far from Los Angeles, is it affected by a city nearby? We have these so-called monarch butterflies. I can't show you too many pretty pictures, so I had to pull in a couple like this. These monarch butterflies, tens of thousands of them pass through Santa Barbara each year. And the biologists wanted to know, where do they come from? What are their migration patterns? Where do they go next? So this is another interesting question that I'll perhaps have time to mention. Is there scientific evidence to support the hypothesis of continental drift? We all believe that is true. Continents are moving, plate tectonics, and so on. And is the Earth's magnetic pole reversal a fact or a fiction? Magnetic pole of the Earth, north-south pole, reverses itself once in a while. I'll tell you how frequently and so on. Is there a pattern to the epicenters of earthquakes? For example, if you observe the earthquakes on the surface of the Earth, is there a pattern to them? Are they clustered at some place? Are they along a line, a fault line, for example? So there's the picture of the Earth. Okay, and is there justification to the sociological theory that more people die after a major event in one's life than before the event? There are interesting empirical studies. Apparently, there is this, empirical evidence, enough evidence to say one can postpone one's death if there is some important event coming up in one's life. Like a child is coming back from America, in Hollywood Bollywood movies, we show this all the time. A mother is sick on her bed, but she doesn't die until the son comes to visit her. So apparently there is enough evidence to say that you can postpone your death if your birth date is coming sometime soon. And in fact, if you look at 2 months before your birthday and 2 months after the birthday, many more deaths occur after one's birthday, apparently. So, this is a statistical evidence. Is there a particular time of day when more heart attacks occur? Look at this graph that I show you here. These are 4 different months, and you see there is a peak around 9 or 10 in the morning. More people die, heart attacks occur at that time. You can see the stress levels increase. So we are talking about a daily cycle. In the daily cycle, there are certain parts of the day that seem to be more stressful for one's life. And so there are, and then is a company cheating on its taxes? Well, let's see how it relates to directions. Is a student copying an essay from another source? Well, we're all interested in this, right? There's all this Google, you ask a student to write an essay and they can Google for it and produce a fine essay. But how do we know if it is his essay or her essay? So how far do the mosquitoes travel from their breeding ground, say a pool of water? This is a very interesting and important question. If you haven't seen a mosquito, there is one there. Okay. So a common theme to all these questions is that empirical evidence for this comes in the form of data that are a set of directions. That's why my title says a matter of direction. Okay, so in many physical and natural sciences like geology, biology, ecology, and so on, one measures directions in 2 dimensions or 3 dimensions. This is a very unusual kind. Sometimes it can be in much higher dimensions. I'll mention about it in a minute. But this is a very unusual kind of data. I'm not sure if any of you have dealt with this kind of data in the past. A direction is, for example, if you have a direction can be 2 dimensions in a plane directions, river flows, for example, birds flying, wind blowing. So those kind of things, you can think of that as a point on the circumference of a circle. And the length of the circle, the circumference of the circle, I take a unit radius, or you can think of it as an angle between 0 to 360 degrees. And I'll show you a graph there. So if you're a mathematician, I can't avoid putting some numbers there. So that is the circle. So you take a circle of unit radius, and every point on the circumference refers to a direction. So when you talk about directions, those are to me points on that circumference. Every point represents a certain direction. So what else was I saying? For example, we're all familiar with statements like the wind is blowing in a northeasterly direction. But if one wants to be precise, we can assign a number between 0 to 360 degrees. What direction is the wind blowing? So there is a directional data is two-dimensional directions. We call them circular data because they happen to be on the circumference of a circle. You can represent them as points on the circumference of a circle. And if you have a three-dimensional data, for you, Earth may be a sphere like this. For me, an Earth is a longitude and latitude. You can represent a three-dimensional direction as a point on the circumference of a sphere. How do we represent, for example, Uppsala as a point on the surface of the sphere with its own latitude and longitude? There are two angles. So there is one angle, a simple 0 to 360, for example, that represents a two-dimensional direction, and a three-dimensional direction can be two angles. One goes from 0 to 360, the other one goes from, we all know the longitude and latitude. We call such data spherical data. For example, if you are referring to earthquakes, where do they occur? They're like points on the surface of a three-dimensional sphere. So they're all, what we call spherical data. So now, there is a serious problem with this kind of data because unlike on the real line, there's no natural zero direction. A circle has no beginning, no end, right? So where do we say zero is, right? So there's a whole big problem with, for example, if the wind is blowing in a northeasterly direction like so, if you talk to I'm trained as a mathematician, so we take the true east as the zero, and we go anti-clockwise measuring things, right? Mathematicians say true east is zero, and then you go that way, and you call that direction 60 degrees. And I've been dealing a lot with geologists, and they tell me that's not the right way to do things. The true north is the zero, and that's called the azimuthal direction. And they come clockwise measuring things. They call the same number 30 degrees. Who is right? Both are right, right? There's no simple zero direction for measuring a direction. It can be, so there is arbitrariness in terms of where you start with a zero and which direction you measure things, clockwise or anti-clockwise. But then if you come to a statistician with a set of numbers, what is he to do? What is he or she to do? So one has to be careful that whatever statistical methods you use should not depend on where you start as your zero, right? I should find out things. This is not a problem with on a real line. For example, on the real line, we can say if you have two varieties of wheat, you can say one variety is producing more than the other. There's ordering on the data. One person is taller than the other. But there's no ordering on this circle. You can't say which one is bigger than which. So there's a lot of issues here. There's no perfect zero. There's no sense of direction to be measured. And there's no ordering. So things are quite tricky here. For example, look at those two directions. If you're a mathematician, that's your zero. You call that 15 degrees. You call that 345 degrees. Suppose two birds were flying in those two directions. And I come to a statistician and ask, what is the average direction for these two birds? We say add them up and divide by 2, and we get right there, 180. That doesn't make sense, right? So it's clear that directional data needs some special kind of treatment. You can't use a sample mean, sample variance, all the standard things we do. I mentioned a bunch of those things, and these may be some of you may be familiar with this: t-tests, f-tests, analysis of variance, all these things that you read in the books, they're all no good. Statistics, in fact, when I first started to work in this field, respectable journals in geology were publishing papers where people were doing analysis of variance and such tests, not knowing those are absolutely invalid. If you measured a different sense, they would get a different answer. So it turns out this is a brand new area to investigate. How does one measure the average, for example, a simple thing like that? Or what is the variation between a set of directions and things like that? So I'm saying here, we need a new set of tools and so on. And I say here, my aim is not to give a tutorial, but just to make you aware that these directions need a special kind of treatment. You need to, whenever you measure directions, you should be a bit more careful. You shouldn't do your standard R package or S plus package that you're used to. Okay, so here is a simple something simple that I'll tell you, and then we'll move on. I won't tell you too many. If suppose there are two directions, say one direction is that what I call alpha 1, and the second direction is what I call alpha 2. The average of these two directions, if I wanted to get, I don't like to add these two numbers and divide by 2. I showed you that's not the right tool. So what I would do in this case is to calculate what is called a resultant of these two vectors. Think of these as vectors and take the so-called resultant vector. That's that R is the, we teach in high school this parallelogram you complete, and that's called resultant. So if you have any set of directions, treat them as if they are unit vectors pointing in those two directions, and then take the resultant vector of those two. And that direction of the resultant vector will do no harm for you. That is the right average for these two numbers. And that kind of thing has all the nice properties. It doesn't matter whether you're a geologist and give them different numbers, or a mathematician and give them a completely different set of values to them. But the resultant vector always points in the right way to direction of the resultant vector is the correct thing. Not only that, it turns out if you think a bit about this, how long will the resultant be? Length of the resultant can be, if you have two unit vectors, if they are right on top of each other, the resultant can be long, right? If the vectors are very far apart, resultant vector will be short. So there is something else cooking there. What's cooking? The length of the resultant is also a measure. The direction of the resultant vector points to the average direction of the numbers, and then the length is a measure of how concentrated the data is. Concentration as opposed to variation. Sample variance. Sample mean, sample variance. We're getting two things in one. The direction of the resultant vector and the length of the resultant vector give you those two measures. So that's the basic tutorial. That's all I want to tell you about this area. So there are these kind of things that one has to do. Circular mean is defined as the direction that the resultant vector takes, and this is immune to what we call the zero direction or the sense of rotation. In addition, the length of the resultant vector, which can go from n points, it can go from 0 to n, and it measures the concentration and replaces the sample variance. And now back to the scientific questions and how they relate to directional data. For example, it's clear that if you, in some cases, the geologist is asking me about this, the directional flow of the river, that's what they call a paleo current analysis. Paleo simply means past, okay, current of the river in the way past. So he had data on two sets of directions, one referring to 1 million years ago, one maybe 2 million years ago. He wanted to know if the river changed its course. So he or she they can measure these paleo currents, and therefore that's a simple measure of direction. He was measuring how the rocks are oriented and so on. So the scientists who work on ornithology record the direction of flight of birds, like these biologists who came to me about these butterflies. He was looking to see which direction they are leaving from Santa Barbara, which way are they flying. They note down and they know. So these bird migration people, they look at this. This is a simple matter of two-dimensional directions. Okay, so I'm only going to tell you that various scientific questions relate to measuring directions, and directional issues can resolve these issues. I won't tell you exactly how they resolve completely, but I told you the averages and variances and so on, things like that are to be done a little differently. Magnetic pole reversal. I give you some numbers here. Apparently, I helped a geologist write a very comprehensive paper recently on this magnetic pole reversal. North-south pole apparently flips completely. South becomes the north and north becomes the south. Once every 450,000 years. It's not every other day, and it takes 1,000 years apparently for the switch to occur. So it's a slow reversal of the north-south pole to the south-north direction. And in fact, I say that the last reversal took place 780,000 years ago. Average time, 450,000. So we may be due for one sometime soon, right? I mean, if you're a statistician and you say, and the average, this should happen, a bus should come every 450,000 years, and it hasn't come for 780,000 years. So that's how do geologists do this? This is a measure of three-dimensional directions that they measure. How do they do this? There is another kind of rock called the igneous rock, which is rich in iron ore. When the lava flows out of a volcano, then it settles down. It's under the influence of the Earth's magnetic field at that time. So Earth's magnetic field, if it's north-south, is the iron ore particles in there record the direction of the Earth at that time. So you see, again, it's called paleomagnetic directions, paleo past again. So this is again a very big fertile field. There are books written on this topic, paleomagnetism. So people can study how old rocks are and what the direction of the Earth was at that time. So this is how one can look at it. This is a three-dimensional direction now. Okay, not one of those that north-south. So pole reversal is apparently it's a well-known fact. It's scientifically studied and so on. So those are some of the facts about the. Now, how about the idea of continental drift? Continents, we all agree by now that continents are moving, and in fact, we believe, Los Angeles, where we are, is on a different plate than San Francisco. And in fact, we are getting 1 inch closer each year to the San Francisco. So that the plates are moving and continents are drifting. In fact, Australia and India used to be on the same plate. At one time, that was called the Gondwana land. And so how do people tell about these kind of things? They study paleobotany, the old botany of the past. That's one way. But statistically, to verify this, you can look at the Earth's magnetic pole, match the Earth's magnetic pole at the same time in Australian continent and the Indian continent. And you can make the corrections and adjust them and see that the rocks match. So that is another evidence, further evidence that there is indeed these two countries were at the same place at one time. So that is another paleomagnetic directions are used in settling this issue of continental drift. Now again, I say it's a matter of directions because it's a three-dimensional directions. Now, here is another issue that periodic phenomenon of a known period, for example, a day, 24-hour day, you can think of that as a circle, 24 hours, and ask, that's exactly what the heart attacks study was about. They were collating data over several days, over a month, 30 days. So you could see which part of the day are more heart attacks occurring. So you can reduce any periodic phenomenon of a given period into a circle of that corresponding 24 hours. Or for example, timing of a surgery. This has been a interesting topic. I said time for taking a medicine. What time of the day is a good time for you to take a medicine? You might have blood pressure and you need to take a medicine. What is a good time? In fact, they say the timing is as important as the dosage, oftentimes in a lot of medicines. And so this has become an important topic, chronobiology, chrono time based, chronotherapy. In fact, there's a big fat book on this chronotherapy on cancer. And for example, if a woman has a breast cancer and she has to be operated for the breast cancer, what's a good part of the menstrual cycle in which the operation will be more successful? And there's a lot of metadata on this issue. And they say the middle of the menstrual cycle is a much more successful time for surgery. So this is again to look at 30 days of the menstrual cycle as a circle and look at parts of the circle that correspond to successful events. Birth, death cycle, and these are all different things where we don't have directions like 2 dimensions, 3 dimensions that I mentioned so far, but in this case, these are cyclical events which can be reduced to circles of a given, day or a month or so on. So that's the, I say it's again a matter of directions here. Now, here is an interesting topic that I should mention. This is, maybe not many of you would have heard of this first significant digit phenomenon. What is this about? You take a big book of large set of numbers, Okay, look at what is the first non-zero number. Zero doesn't count. So that's called the first significant digit. If it is 0.025, 2 is the first significant digit. Okay, 35 million, 3 is the significant number. So if you look at these numbers 1 through 9, how frequently do these numbers occur? 1, 2, 3 up to 9, right? What would our intuition say? These are numbers, right? They are all over the place, 1 through 9. So one would think they must be equally likely. But it turns out there's a guy named Benford who in the 50s did a interesting empirical study. He looked at hundreds of Reader's Digest volumes, the magazine Reader's Digest. So he looked at every number there is on that Reader's Digest for several years and counted how many times this one occur, how many times two. And so he found a very strange thing. One occurs much more frequently than two, and so on and so forth. In fact, I say here, one occurs 6 or 7 times more often than 9. And there is something to do with circles here. I won't complicate the issue, but I want you to see that there's a relation to circular data which says that the numbers, for example, this is something called Benford's law, because Benford was first to have discovered this empirically. But there's a lot of mathematics behind it. There's something about circular distributions that says for example, the numbers 1 through 3, between three of them should have 1/3 chance out of 1 through 9, right? But instead of 1/3, they have 60% chance that the now significant digit will be 1, 2, or a 3. Not as likely for 6 or 7 or 8 to be the first significant digit. So this is one of those things that people often use. I'm told the Internal Revenue Service in USA, that's our tax people. They look at your tax documents and see if your numbers follow this pattern. If not, there is something to be suspected about what you did. Maybe you cooked up your books. So I say, for example, this is one check that can be used to verify a figure submitted by an individual or a country, say, for example, Greece when entering Eurozone, are really genuine, right? You might manufacture some numbers because thinking, oh, this number should be equally frequent and so on. But this is a auditing test of some kind. So that's, again, it's related to the matter of directions. And well, I guess I need to move on faster. Okay, plagiarism and latent semantic analysis. It turns out if you give me an essay, I can look at the frequency of words used there, frequency of how many times do you use a certain word. And there is a dictionary that I can make up, and then we calculate frequencies. And that can be reduced to a vector in a hypersphere. And so any text that you put out is a point on this hypersphere, not in 2 dimensions or 3 dimensions, but in very high dimensions. So if you look at 2 points, if they're pretty close, the essays are very similar. So one can look at the closeness of 2 essays to see if someone is actually copying from someone else. And, Shakespeare wrote the same play as some new, if you discover a new play, this is one of those things in literature. Someone discovers a new poem, is this written by Shakespeare? Things like this. So one can sort it out. And this has to do with, again, a big hypersphere. Okay, now how much time do I have? I'm already running out, huh? Okay, I'll tell you quickly this little thing about mosquitoes and isotropy. I guess we started 2 minutes late. So, okay. Anyways, okay, here is something interesting. There is I'll get to the story here. Okay, the story is there's a man named Ronald Ross. He actually won a Nobel Prize in 1902 for connecting mosquitoes with malaria. And he was the first one to have said malaria is carried by mosquitoes. And he lived in my hometown, Hyderabad. He was a Britisher, but he was born and brought up there, and mosquitoes are plenty in Hyderabad. So he did this research and he found this connection, got a Nobel Prize. And then he asked this following question too: how far do mosquitoes move from where they breed? A water pool, for example. How far do they go? They seem to go buzzing in arbitrary direction. You go some length and then you go, twisting again and so on. So how far do they go from a pool of water? You don't find too many mosquitoes too far away. So this is what I call a random walk of some kind, that a mosquito goes like so and then twists around a bit in an arbitrary direction, goes around another bit and then twists around. So in such segments of, if you would say, for example, if a mosquito walks 100 such segments, how far will it be? Suppose each segment is 1 foot in length. How far will it be from where it started? If it went 100 segments, each of 1 foot, it can go continuously 100 feet away, right? If it is smart, if it is planning to go in a particular direction. But if it is buzzing off at random, how far will it go? This is a question he posed to Carl Pearson, who is one of the preeminent statisticians of the time, and is known as a Pearson's random walk problem. Although, as I say, he didn't, question was not his and answer was not his, but he got the credit for posing this problem in any case. Okay, so there are a lot of interesting questions, physics, chemistry, and so on, polymer chains and how long a chain would be. And I shall cut short my discussion and tell you that this is a short table that tells you, for example, if you have 100 segments of 1 foot each, 95th percentile of the length that you can be from the origin is 17. What does 95th percentile mean? That means 100, this is what, if 100 steps of 1 foot each, if they are flying in random directions, 95% of the mosquitoes will be within 17 feet of where they started. So in other words, the chance that if a mosquito flies 100 such segments, that the chance that it will be more than 17 feet away is only 5%. Only 5% of the mosquitoes can get farther than 17 feet. So they stay pretty close to the pool of water. This relates to directions of flying and so on. So it's a fairly complicated equation. So the expected length is only 9 feet. Think of feet. Okay, each 1 foot segment, and then 9 feet is how far it will go on the average. And 17 feet is the maximum 95% of them will go. So we have a interesting thing in California. If you are driving drunk and a policeman stops you, he asks you to walk at a straight line. And so, I mean, if you walk straight, I say here that if your statistical test for drunk driving, if you release this person, if you ask him to 100 steps, and if he goes more than 17 feet away, statistically he is not fully drunk. So, right? So this is based on the theory that, okay, now I'll end my talk by saying, some of you noticed my long name, Srinivasa Rao Jammalamadaka. Actually, I was known for a long time as simply J.S. Rao. From the part of India where I come from, my family name, Jammalamadaka, is written in the beginning. And Srinivasa was my given name, Jammalamadaka Srinivasa Rao. Jammalamadaka is the family name. And I was known as J.S. Rao. That's how the Rao spacing tests and Rao's tests of homogeneity, all these things were named after me, and my last name was a Rao, although it was not real last name. It was in the last place, happens to be. Okay. And then when I went to America, Americans said first name, middle name, last name. For them, last name meant a family name. So I had to change my name to Srinivasa Rao Jammalamadaka. I changed Jammalamadaka to the last place, as it should have been in the American system, right? So I have both these names, and people often ask me this question. So I have an explanation and a circle. If you are a geologist and going this way, you start with a true north and say Jammalamadaka Srinivasa Rao. But if you are a mathematician, you start at the true east and go this way, Srinivasa Rao Jammalamadaka. Circles again. Okay, that's is again a matter of direction, I said. Okay, and here is a little book that I wrote on this thing called Topics in Circular Statistics that gets into some of the interesting problems and more mathematics on this and so on. I'll end my talk here. Thank you.